previous module, we were talking about non-degenerate perturbation theory. We derived equation for the first order correction to energy and first order correction to the wave functions, and this was the slide where I left you. And for the first order correction, what I said you that En1 will be equal to integral of psi n naught, then the perturbation which we introduced, again psi n naught d2. So the correction to the energy one can find out by knowing the wave function for the unperturbed system and the perturbation. That's all. Okay. So this will give you, and the total energy for the perturbed system will be energy of the unperturbed system plus the first order correction which we have determined. So total energy will be this one. And this is the relationship for psi n1, that is the first order correction to the wave functions. So and if you look at this one, these perturbations are very small. So what is expected is that the change in the wave function or change in the energy should be very small after the correction, and it means correction term should be very small. So if first order correction to the wave function has to be small, and this is the wave function for an unperturbed system. Psi m not is written, so it is for the unperturbed system. So this cannot be a small. What has to be a small is this term, summation term. So this summation term should be less than 1. Then only we can apply the non-degenerate perturbation theory to a particular system. Now this condition is not satisfied when En naught is equal to Em naught. What does it mean? Em naught means we are talking about degenerate system. So if it is degenerate system, then the condition of this being very small is not satisfied, and we say we need a new approach, a different approach for doing this. Once we have the relationship psi n1 and En1, first order correction to energy and first order correction to the wave functions. I have given you in the previous slide second order correction to energy also, but we will not do. Now we will see how can we apply these equations to a particular specific problem. So let us see this problem. This is an issue where I said you that an electron in a one-dimensional box of length L is placed in a uniform electric field of a strength F is an example of perturbed system. It's the same particle in a one-dimensional box which you have done, no change, but now the electric field is being applied to this particle in one-dimensional. Obviously, we are supposing that the particle is charged particle, then only it will interact with the electric field. Okay. So if it will interact with the electric field, a force will act on the particle, and because of that force, there will be some potential energy. Ideally, what we have done in particle in a one-dimensional box is this, that within the box we say potential energy is equal to 0. Okay, the potential energy within the box is equal to 0. Now we say that okay, potential energy is not 0 since we are applying an electric field, so there will be some force acting on the particle, and because of that force, there will be some potential energy. And what we have to calculate is first order correction to energy and first order correction to the wave functions because of this particular change in the potential energy of the system. If you have a particle in a one-dimensional box, what you know that the Hamiltonian for a particle in a one-dimensional box could be written as h naught minus h square divided by pi square m d square by dx square. And then psi n naught is also known to you. It is normalized wave function of particle in a one-dimensional box, could be written as root 2 by L sin n pi x divided by L. And the energy of the unperturbed system is also known, n square h square divided by 8 ml square. So the change in the value of this unperturbed wave function and this unperturbed energy we have to calculate up to first order only, okay. So how will you go for doing this? We say that the system is perturbed because of the electric field. So the force acting on the if we suppose the particle has a charge E present, then the force because of this electric field will be EF, and the potential energy because of this force will be EFX. So the force is proportional to the value of x, and the particle one-dimensional box is an unsymmetrical box from x is equal to 0 to x is equal to a, and potential energy V is equal to EFX. Okay. So at x is equal to 0, at this point potential energy will be 0, and at this point the potential energy will be EFA, or so, the question is L, so EFL. Okay, so EFL will be the potential energy at this point, and 0 will be the potential energy at this point. Okay, so what does it mean? As you move away from x is equal to 0, the potential energy goes on rising. It's proportional to x. Okay, and this is what is perturbation. This EFX is the perturbation, which is shown as, which we show as H prime is equal to EFX. Now, the Hamiltonian for the perturbed system we write like this one, so that you know EFX. But this is there is no use of these relationships, because we already have a relation for the first order correction to the energy. So we will use that first order correction to the energy relationship. This is the energy relationship, first order correction, psi 1 naught H prime psi 1 naught d tau, and psi 1 naught will be what? Root 2 by a sine pi x divided by a. It's root 2 by L sine pi x divided by L. Then for H prime I have written EFX, and again psi 1 naught, so root 2 by L sine pi x divided by L will be the first order correction to the energy. E11 is the first order correction to the energy. Okay. So we have to solve this one. You can bring these two, root 2 by L outside. You can also bring EF also, because charge on the particle and the force which field which we are applying are also constant. So if you bring it outside the integral, we can write this one, 2 divided by L multiplied by EF, it will be outside the integral. Now you have to integrate from 0 to L sine pi x divided by L, x sine pi x divided by L, and it will be x sine square pi x divided by L. So it will be E11 will be 2EF divided by L, x sine square pi x divided. This integral we have to solve. Okay, sine square pi n pi x divided by L dx that you have done already, but it is x into sine square pi x divided by L. So let's do it, and we will do it through by changing the variables. So we suppose this pi x divided by L to be y, and then if you rearrange x, you will get YL divided by pi, and therefore the dx will be L divided by pi into dy. So if pi x divided by L is equal to y, then when x is equal to L, y is equal to pi, and when at x is equal to L, y is equal to pi. So even the limit of the integral will change. So what will be the now integral, new integral? 2EF divided by L will remain. Instead of x, I have written YL divided by pi. X is this one, YL divided by pi. Okay. Then you have dx. Dx is L divided by pi dy. So this is your dx. Okay. Now pi x divided by L is y. So pi x divided by L, well, this pi x divided by L is this one, y. Okay. And the limit will be 0 to pi, because y at x is equal to L, y is equal to pi. Okay. So this differential if you solve, this integration if you solve, then it is very easy. So again L by pi and L by pi you can bring outside the integral. So you have y sine square y dy, and we have the standard integral for y sine square y dy, and that standard integral will give you pi square divided by 4, and if you put this value, what do you get? You get pi square divided by 4 means 2 EFL divided by 2 is the first order correction to the energy of a particle in a one-dimensional box placed in an electric field of F, a field strength F. Okay, and so corrected form of the energy will be what? If you write the corrected form, the first order correction to the energy is this one, but the total corrected energy will be h square divided by 8m L square, because n square will become equal to 1. We are talking about the ground state. Okay, so it will be E total will be h square divided by 8m L square plus EFL divided by 2. Okay, now once we have this one, the second thing which we have to do is we have to find out the first order correction in the wave function, and first order correction to the wave function also we can do by the same the relationship which I have given you, and this is the relationship. Now you see it is summation term, m not equal to 1. Okay, I said you if m is equal to 1, then it will be E1 naught minus E1 naught, and then this will be very high value, okay, which it should not be, and it will be a degenerate system. So degenerate perturbation theory is another theory about which we will talk about later on. But this E1 naught E1 is not equal to m, means, but m could be 2, 3, 4, 5 and so on. So this summation is a long term where different terms you will have to write, and each term you will have to calculate for finding out the psi 11. That is first order correction to the wave function for this perturbed system. And if you expand this summation for a few terms, then you can write it like this one, okay, because you see the first term will be E1 naught minus E2, and here you will have psi 2 naught. So psi 2 naught is also known to you because it's for the unperturbed system. Then the second term will be E1 minus E3 naught, E1 naught minus E3 naught, and here also it will change psi 3 naught, that's also known to you, okay. And here also you have E1 naught minus E4 naught, and it will be psi 4 naught. So this is also known to you. So at all these places, this is known to you, this is known to you, this is known to you, this is known to you. All has naught symbol, so there is nothing which you don't know. All is known to you because all data is from the perturbed system, and it's a solvable problem. We have solved this problem earlier. Now we cannot do simultaneously all these terms, first term, second term, third term. So what we will do, we will start with the first term only, okay. And if you write the first term, then first term will be in the limit will be 0 to L, then psi 2 naught H prime psi 2 naught, psi 1 naught divided by E1 naught minus E2 naught. So this is the first term, and even the first term psi 2, this is your first term, which I have written here, okay. We have for the time being we are not concerned with the second and third term, and moreover higher terms also could be there, but I will tell you how we can reach at the final value, okay. So if it is psi 2 naught, then it will be root 2 by L sine 2 pi x divided by L. So this tells you the quantum number, and it is psi 2, so the quantum number is 2, okay, that you know n pi x divided by a, n is the quantum number. Then this is your perturbation term EFX, and then again root 2 by L sine pi x divided by L. It means you have 1 here, which is your quantum number, okay. So this is your numerator. In the denominator you have energy values, and energy value you know for particle in a one dimensional box is E n square h square divided by 8m a square, okay. So E1 will be n square will be 1, so h square divided by 8ml square. So sorry, I am writing 8 time and again 8ml square, and then you have E2 is equal to n square will be 4, so 4h square divided by 8ml square. So what we have to do, we have to find out the integral in the numerator, and the denominator is very simple. Psi 2 naught is also known to you, okay, for the finding of the first term. So let us see how we do it, okay. Again in the numerator, if you look at the numerator, it's the same. What I have done, 2 by L I have taken outside, root 2 by L from here, root 2 by L from here, so it will 2 by L. EF also I can take out, and this x is from the H prime. This x comes from the H prime. I could have written it earlier also. So this becomes equal to 2 EF divided by L. Left hand side is same, so don't bother about that. 0 to L sine 2 pi x divided by L and sine pi x divided by L x dx. And if you subtract in the denominator, that is minus 3h square divided by 8ml. Obviously this will be a higher value, this will be a lower value, so it is minus 3h square divided by 8ml square, okay, into psi 2 naught. Now instead of writing all the relationships time and again, what I have done, I did first I will do this integral in the numerator. So integral in the numerator is what? Sine 2 pi x divided by L sine pi x divided by L into x into dx, okay, x dx. Now again what you do, you change the variable. Pi x divided by L is y. Okay. So x is equal to YL divided by pi, same way as we did earlier, and therefore dx is L divided by pi into dy. And if you put these values, then your sine 2 pi x divided by L, sine pi x divided by L x becomes equal to pi x divided by L is y. So it becomes sine 2y. Okay. It will be sine y. Then x is YL divided by pi. This x is YL divided by pi, and then dx is L by pi into dy. Okay. So this change we did, and again for the same reason it is 0 to pi, which I said you earlier. It's 0 to pi. Okay. So what you can say, this also I should have. Now I can bring this outside, L divided by pi and L divided by pi outside the integral. So L divided by pi square y sine 2y sine y dy. Okay. And now what we can do is 0 to pi y sine y into 2 sine y cos y I can write for this one, sine 2y. And then this will be what? Sine 2 I have taken outside, so 2y, and then sine square y I can write as 1 minus cos square y, and then 2 cos y. So you have y cos y dy, one integral, and another integral y cos cube y. So it is like this one. Okay. So this integral you have to solve, and this integral you have to solve. Of course it will be okay, like this one. So if you solve this integral from the integral table, what you get is solution is cos y minus y sine y from 0 to pi, and this comes out to be minus 2. Okay. And if it is minus 2, and for the one integral, for the second integral y cos cube y dy, again you solve it from a standard integral, and what you get is minus 14 divided by 9. So if the two integrals, if you put these values, 2 L divided by pi square minus 2 plus 14 divided by 9, what you get is minus 8 divided by 9 L by pi square. This is the integral in the numerator, which I have shown you in the earlier slide. Okay. So this is only the integral part. If you go for the full solution, beyond the integral, you have 2EF divided by L also. So you put the values from the integral using the value from the numerator integral. Everything is same. This was the value of integral. So we can write it like this one. And if you solve this, what do you get? You get 0.48 into EFL ml square divided by h square pi psi 2 naught. Okay. So you see, the first order correction to the wave function of a perturbed particle in a one-dimensional box, we have obtained this correction. It's a constant 0.48. EFL is also, everything is constant. Mass of the particle is constant. Length of the box is constant. H square is constant, and it depends upon the second wave functions. First order correction to the ground state is depending upon the wave function of the first excited state of the particle in one-dimensional box. Of course, it is known to you, but this you should mark, that correction to the ground state of the perturbed system, for this to find out, you require first excited state wave functions. You do have the wave functions, we can do this, but we will stop here. What about the other terms? Why I have written psi 11 up to this only? We said that the similar calculations for the summation, for higher terms of the summation can be done. But when you go for the higher terms in the summation, what is written here? Let me go back to the equation. Okay, this was. Okay. What is this? E1 minus E3, E1 minus E4. So it is the difference between the energy levels. And as you go to higher and higher terms, this quantity will be very large. And if this quantity in the denominator will be very large, the overall quantity of the value of this term will be very small. So you always need not to go for many higher terms. Okay, and one or two terms is enough for calculating this one. In this case, the second term will become equal to 0. So the third term we will not calculate, and the final value we suppose as E11 is the same as we calculated to be equal to this one, 0.48 EFL ml square HS divided by HS square psi 2 naught. Okay. So we say that the same thing is there, E1 naught minus E4 is quite high. Okay. So this way we found the value of, so when we do the calculations, this we don't need to calculate the higher order terms. The lower order terms is enough, and then the corrected perturbed wave functions could be written like this one: psi 1 is equal to psi 1 naught plus 0.48 EFL ml square h square psi 2 naught. Okay, and corrected energy also we got. So what is the important relationship in the non-degenerate perturbation theory? The important relationship in the non-degenerate perturbation theory is En naught is eigenvalue of the unperturbed system. From this you can calculate the En1, that is first order correction to the eigenvalue or energy, and then psi n1 you can calculate for first order correction to the wave functions. So for second order correction to the energy, we can again use the similar relationship. We have not derived this, but I have given you the value because it's very rarely used. But you should use this one. This equation I have given you without derivation. Okay. So these three relationships you must remember. Then what we do is we take another problem. So we calculated psi 1 for this perturbed system, and the higher order terms we will not calculate. I said you the why we don't calculate. If we write the, for this perturbed system we calculated the psi 1, that is first order correction to the wave functions, and I said you because E1 minus E4 will be very high, so the ratio will be very small and we need not to calculate higher terms. This term is enough for giving the approximately good wave functions. So if you write the first order wave functions for the perturbed system, how do you write? You take the ground state wave functions for the unperturbed system plus the perturbation which we have calculated because of the presence of the electric field strength. So this is the way by which you have to do problems based on non-degenerate perturbation theory. First order perturbation to the energy you can calculate, first order perturbation to the wave functions you can calculate, and then you can write the corrected wave functions and corrected energy of the perturbed system. Okay, and for these the three relationship which is important for you to at least remember always is that since En naught is the eigenvalue of the unperturbed system, so En1 we can calculate by using the wave functions of the unperturbed system, and first order correction is given as integral of psi n naught h prime psi n naught d tau. Then first order correction to the wave functions we just calculated from this relationship. Second order correction to the energy also can be done by using the wave functions for the unperturbed system. So these three relationships are important, which you should always remember. If you go for doing for another problem, then this is a situation in which the particle in a one-dimensional box is perturbed and a constant perturbation is applied from the 0 to a by 2. It's an unsymmetrical box because we start from 0 and we go to a. So a constant perturbation is being applied here, and for this value to calculate, again we will use the first order correction to the energy. We will do the correction to energy only, and if the perturbation is a constant perturbation, V naught, it is not changing with x. It is throughout from 0 to a by 2, it is constant. So psi n naught is again root 2 by a sin n pi x divided by a, and perturbation I have given you, so En1 you can calculate. If you write the En1 value, it is this one, and when you calculate this integral, what do you get? The integral you can calculate very easily because we have already done it. Root 2 by a and root 2 by a will be outside the integral, so it will be 0 to a 2 divided by a. Okay, and then you have V naught, which is also a constant, so we bring V naught also outside, and then you calculate the integral is sin n pi x divided by a, sin n pi x divided by a. So it will be sin n square n pi x by a into dx, a by 2. Okay, And this integral you have already done when you did the normalization of the particle in a one-dimensional normalization of the derived wave function for particle in a one-dimensional box. How did you do? 1 minus cos 2n pi x divided by a, you write. So this integral you can write as 2 v naught divided by a, and then integral of 1 minus cos 2n pi x divided by a into dx, okay, divided by 2, and so on. So this is already done there. I will omit this one. You practice it yourself, okay. Okay, so you practice it. Now once you have this v naught divided by 2, then a constant perturbation, we have a shortcut method of calculating the perturbation for constant perturbation if it is applied to asymmetric potential well. Means well length is from 0 to a, not from, if this is your well length 0 to a, or you can, for the same length, what you can write is minus a by 2 to plus a by 2. This is called symmetric potential well, and this is called asymmetric potential well. So if you have asymmetric potential well, then you can calculate from asymmetric potential well this particular relationship can be used. Okay. So this particular the relationship is En1 is equal to the strength of perturbation into length of perturbation divided by length of well, and from this one can calculate the perturbation first order correction to the energy. And for this, an example is this one: from 0 to a by 3 there is no perturbation. From a by 3 to a by 2 there is a perturbation, again a constant perturbation alpha, and from a by 2 to a there is no perturbation. So the potential energy is perturbed between a by 3 to a by 2. This will give you the length of perturbation. So if you use this shortcut relationship for finding out the En1, then perturbation is alpha, length of perturbation you get a by 2 minus a by 3, and then you divide it by a, you get the value equal to alpha divided by 6. Okay. So this is a shortcut method, but remember the perturbation should be constant and the potential well should be asymmetric. These are the two conditions, then only you will use this one. Okay. Otherwise you will not this one. Otherwise you will calculate the integral. Okay. Then again, if you have this problem, if the value of perturbation is Vx divided by A in a 1D box having length 0 to A, what is the total energy of the system? Here the perturbation is not constant. You see, Vx divided by A means perturbation is not constant, and this you have already done. Efx was the non-constant perturbation, so it's like this one, Vx divided by A, and if you calculate for this, H prime is Vx divided by A, psi n naught, again the same thing. So your En1 will be Vx divided by A, and again you will have to find out x sin square n pi x divided by A integral, and x sin square n pi x divided by A dx you have already done, it is a square by 4, and this comes out to be V by 2. So the total energy of such system is En naught plus En1 is this one. Okay. So these are the few problems which tells you that for non-degenerate system, how would you apply non-degenerate perturbation theory to calculate the eigenvalue or correction to the eigenvalue, correction to the eigenfunctions. Okay. We will see some more problem on in the next module, and then we will start doing the degenerate perturbation theory in the next module. Okay. Thank you.